We are
Yeah.
now on time to start, so it's my pleasure to host one of today's Ask Me Anythings with Alex Aiken. So please feel free to enter questions in the Slack channel. And we already have a bunch of questions entered, so we will go ahead and get started. So the first question is from Sebastian Peters from TU Eindhoven. He asks, with Stoch demonstrating the applicability of stochastic processes during program construction, do you see a future where it will become mainstream to use these types of processes during the build process, be it during or post-compilation?
I think that will happen eventually, at least in some domains. The challenge there is, of course, the correctness. So I think what projects like Stoch have shown is that we can build programs, or at least small pieces of programs, via some kind of search procedure, where we don't know, where we just get guided by some cost function that's partial. But then in the end, you have to still know that this is going to work in every situation. And I think there may well be application domains where you don't actually care that much about absolute correctness, and those will probably be the ones where this stuff becomes mainstream first. But for a lot of the things that we think about every day, it's really the verification technology to show that it actually is reliable and that you can believe the results that will determine how much uptake it gets.
So how do you see that verification coming together with the stochastic process?
So, well, the part that the way we've been approaching it is just to decouple these things completely. So you do the search and you get something, and then you have a completely separate verification process. And of course, from a research point of view, that's great because you have this program you don't know anything about, so it's a very challenging problem. All kinds of interesting things come up, especially with respect to the assumptions you can make for things like invariant inference. And it also has some other advantages in terms of decoupling what's hard into two separate problems, I think. But that's not the only approach that one could try. And I think one of the interesting things that it really hasn't been tried is more constrained kinds of searches where you do know some properties, and then your verification problem is easier. All right. If I was going to zoom out a little bit and just talk less about Stoch specifically, I think the bigger issue here is that it's just way too hard to build compilers, okay? And it's just way too hard to build our tools. So if you look at the rate at which machines are changing, so the rate at which the hardware advances, actually the software tools on top are not evolving as quickly. So if there's a new generation of hardware, which is actually fairly significantly different every couple of years, we can't take 10 years to build a compiler for it, right? I mean, you're just not keeping up then. By the time you've built the compiler, the hardware has already changed again, all right? So we need to get better at automating the process of building our tools. And compilers are just one example. There are lots of other tools that where we would benefit if we could somehow do that more quickly. And I think that's a big challenge, and one of the things that Stoch was trying to address.
So how do you think about what should we be thinking about to do that automation? Like, how could we make it faster to build compilers?
Well, I think so. So in the case of Stoch, it was automating the search, automating the optimization process, and trying to consider, instead of having lots of individual passes, all of which is a beautiful algorithm that solves a specific problem, but you have to build 50 of these things to have a reasonable compiler. Just have a great big search problem where you kind of consider all the constraints simultaneously and do something, in the larger space. All right. And, I don't know that, well, I'm not going to claim that that's feasible, for the scale of things that traditional compilers do. I mean, Stoch was looking at very small pieces of code and achieving those kinds of goals. But I think that's the general direction where we're going to essentially replace multiple components with things that spend a lot more compute and are a lot less efficient in the traditional sense, and solve a joint optimization problem over several of these phases simultaneously. I think that's a good way forward. And since the optimizer is probably both 90% of the time of the runtime in a compiler and 99% of the engineering effort. Actually, I shouldn't say it's 99%. There's a lot of other stuff in a compiler too, but it's a significant chunk of the engineering effort. Even if we could do a better job of building optimizers more quickly, I think we would be in a better place than we are now.
Makes sense. So a follow-up question that Sebastian asked was, with how similar your recent work in ML is compared to what you did before, what caused you to move into a machine learning direction?
Well, that is absolutely a great question. And I will say that, I've kind of resisted the gravitational pull of machine learning for a while. I've never really been somebody who, wanted to work on the thing that lots of other people were working on. Not that I didn't want to work on it, that wasn't a thing for me, and so it was really my students, who pulled me in that direction, right? And this is what typically happens. I mean, you think you know what you're doing, and then it turns out your students are doing something else, and you wind up doing that because they're the ones who are actually doing it. So in the end, you don't have a choice, and so you're the leader. You have to follow them, right? So.
Indeed. John Wickerson from Imperial College London asks, what's the research idea that you're most proud of?
Oh man, that is a really loaded question. Or a good question. Yeah, I don't think, in some ways I like a lot of different things that I've gotten to work on. I don't think there's anything that maybe sticks out among those that I would have trouble picking. I mean, the comment I would make in response to that question is, it's always a surprise to me how I view the work and how others view it. Okay, and often there is a gap. Let's put it that way. All right. So some things that I thought were nice, but maybe not that important. People reacted very strongly to and very positively to. And other things that I was really, really loved, for some specific aspect of the work. Let's say they're underappreciated still. All right. So, I've enjoyed it all, and continue to. That's probably all I should say. Yeah, I honestly would have trouble answering that question.
Mike Hicks from the University of Maryland asks, you've had consistent, sustained success at mentoring students into top researchers. What are some key elements of your mentoring approach? And many people have upvoted this question. They all want to know what your secret sauce is.
Yeah, so I anticipated that people might ask about, it's about working with students, and I thought about it a bit, and the truth is I don't know. Okay, I don't want to give a non-answer to this. But I find out, every student is different. Okay, I have not discovered a formula that works, for every student. I do come with an attitude, I think, when I work with a student that we're really partners. Okay, it's not. I don't want to be in the position of telling them what to do. I want to work together, and that's from the beginning. Okay, so I try, even with very junior students, I think I probably give them a little more scope than maybe is best, in terms of productivity at the beginning. And the one thing that I do consistently is I have a model of a student as a kind of incomplete researcher. So there's a talk I give with a list of skills that you have to learn to be a researcher, ranging from very concrete, like how do you write a paper? How do you structure an experiment? How do you prepare a talk? I mean, what's a good, how do you prepare slides that look good? And all the way up to how do you pick research problems as maybe as the most high level skill that I think is the most difficult one to acquire. And I do have in the back of my mind, I think most of the time, an idea of where the students most need to work on these things, and to help them at the beginning. I really view it as my job to kind of fill in those places where they're weakest. So so maybe the first paper we do together, I write a lot of it, or I'll prove the theorem, or I will design the experiment, whatever it is that they don't know how to do. So they just don't get stuck and we don't fail to finish something. I'll try to step in and do that part. Okay. And then I find that once they've had that first successful experience, and once they see end to end, how you cradle to grave, how you take an idea and they go all the way through to the talk at the conference. that they gain the confidence and experience, and they can do it again with a little less help. And then we just try to repeat that, and at some point, there's liftoff, and they don't really need my help anymore. And they, and I'm really just advising, after that. But that's when things go well, I think that's how it works for me.
That makes sense. The obvious follow-up question is, how do you teach them how to pick research problems, which was one of the skills?
Yeah. So I'm a firm believer that there are some things that can't be taught. They can be learned, but they can't really be taught. Okay. And how did I learn to do this? This is the only way I know how to answer this question, because I think it's a bit of a mystery. All right. And for me, it was really just being around other people and seeing how they picked research problems. So having colleagues and watching their projects. And there were many times early in my career when somebody would come to me and say, I have this idea, I want to do this. And I would say, oh, go for it. And then I would think to myself, that'll never work. Like that's the worst idea. And then like 6 months later, they had a project and it was actually making progress. And maybe a year or two later, there was a really good result, and they were successful. And you learn by observing that, especially about being wrong, in your opinions. I think you learn to have, first of all, have a little more humility about what makes good research, but also about what I think the hardest thing maybe for a new student or somebody early on to appreciate is how simple research ideas are at the beginning. Okay, because until you do the work, the technical sophistication isn't there. At the beginning, it really is just a simple idea or an intuition, and it doesn't sound like there's really much. And if you compare it to a published paper, and just like all the polish and all the depth that's in something that's been worked on for 2 or 3 years, there's no comparison. You think, this is weak, this is shallow, right? So not dismissing those simple intuitions, and in some ways, the simpler the idea, the better, right? Because at least it's clear, what you're trying to do, and complicated ideas tend to not do as well, especially if your idea is already kind of, has several moving parts at the very beginning. That's a lot harder to turn into something that you can actually sink your teeth into, I think, right? So I think maybe that's, for me anyway, that was what I learned, and I think that's what the students pick up too. But so much of this is not really intellectual. So it's not really about technical ability or about the breadth of knowledge. It's about about learning to trust yourself and to trust your intuition. Okay, and so it's a much more maybe an emotional thing, and not being too quick to dismiss ideas.
That makes sense. Thank you. So the next question is from Haiping Kai from Washington State University. He says that given that most software is written in multiple languages, is it important to develop dedicated program analysis techniques that model and reason about holistically the behaviors of multi-language software, i.e. across the different languages used? Do you think that this is a research problem or more of an engineering issue, for example, by analyzing each language individually and then stitching the results together?
Yeah, so this is a fantastic question. I think it kind of gets to one of the fundamental issues in our field. All right, so so I'll talk to the general issue first and then to the specific question. So programming languages is a field that's kind of divided by its languages. So people tend to work in one or a few languages, even at the research level, and the communication between the different people, say, working on an analysis for Java and people working on analysis for C or for Python or for whatever other languages are the focus of effort of the day, is not as good as it should be. And that balkanization is a result of just reflects the reality in the world, which is in the question, which is that real software is written in multiple different languages, and it's hard to find even a modest-sized system that doesn't involve really a half a dozen languages when you start including the scripting and the shell languages and the make files and things like that. Okay. So to the question whether trying to do holistic analysis across languages is a research problem or an engineering problem. Yeah, so I think this kind of gets to I would turn that back to the questioner. So you make it into a research problem. Okay, so it's a real problem, and the challenge is what is the research problem that is in there. So engineering, when you say something's an engineering problem, in my mind, that's an excuse for I haven't thought hard enough to extract the nugget of research contribution. Now that's a little bit unfair. I didn't. It sounded a little harsh, but I think often in big messy engineering problems, in big messy problems, let's just say there are research issues, and the challenge I think specifically with this one is how can you reduce that to a scale that you can actually do something in a small research group. So it's hard enough to build tools to handle one language, and so if you want to handle even two, I mean, did you just double the engineering effort for your project? Okay, and and two would seem like the minimum to address this problem. Like if you were going to publish a paper, I think referees would probably not be pleased if you did multi-language research in one language, right? So you have to get over that. You have to get over that hump somehow, and that's the challenge. I think like how could you do this in a way that you could actually conduct the research in a reasonable way in multiple languages, in a reasonable amount of time with a couple of students or something like that. And if you can solve that problem, that means that you're more effective than what people are doing in multi-language work today in to build systems. And so probably you're onto something, right? If you can crack that nut, and actually do the research in a reasonable amount of time, that means that probably it has real value, in the real world, or at least it's plausible that it does. So I think it's an important problem. I don't know. I mean, I'll say I don't want the follow-up question. I don't have any idea how to do that either. All right, but I think it's it is something to think about, and I have thought about that. That is an obvious large challenge for us.
I wonder if it's related to your question, your observation on the first problem about we need to be able to build compilers faster. And we need to be able to build tools for different languages faster so that we can do this multi-language research in a way where we're not spending all the time on the overhead piece as opposed to on evaluating the new idea.
Yeah, absolutely. I think I think that's a great comment. I would only say that I think that is one way you could address this problem, right? Maybe there are other ways, right? There might be other approaches that would help, ease the burden of trying to get software across multiple languages to work. And there is, and I think this is a very important problem. So I'll just say one more thing about it. We spend a lot of time thinking about correctness in our field. I mean, it's one of the touchstones of the field, right? So we work very hard to build tools that provide guarantees to people. We're not perfect at it, but I think compared to other fields of computer science, we're the ones who actually care about this stuff, right? And then so we produce all these tools that that actually are pretty good. I mean, generally speaking, the stuff the programming languages community builds and the stuff that that the people who consume our ideas build, they work pretty well. But then we paste them together into these multi-language systems, which have no guarantees whatsoever, right? Because there's nothing that enforces anything across those boundaries, and who knows what's happening, right? So, and actually, a lot of the problems in real systems are exactly at those interfaces.
Indeed. So just a time check for people. We're actually at the end of our scheduled time. The next session for PLDI is starting. So if you wanted to catch technical talks in the session, now is the time to move over to the paper section. There's still a bunch of questions, and Alex has indicated he is available for the next 15 minutes or so. So we'll go ahead and continue. So you're welcome to stay with us, but if you want to go catch the technical papers, now's the time. So next question from Chiran Zhang from Georgia Tech. What's your advice on managing risks in research?
Yeah, that is a really good question. And I actually have a definite opinion about this. So when I start a research project, and there's usually a period at the beginning where it's not really clear what we're doing at all. All right, so there's a period of just kind of fumbling around, trying to figure out how to structure the problem. But at some point, relatively quickly, there's a list of things to do. okay, or a list of problems to solve, all right? And you absolutely want to put the riskiest ones at the top of the list. Okay, you want to do those first, all right? And it is so easy, for a student especially, to fall into the trap of saying, well, I have no idea how to do this really hard thing, so I'll work on this easy thing, okay, because I know how to do that. And so the tendency will be to do all the things that are relatively easy to solve first, and that will take some amount of time, okay? And then when you're done with that, you still have the thing that really matters, right? And you've basically spent a bunch of time and haven't actually cracked the thing that's going to make or break the project, right? So you absolutely want to focus on that risky thing first and force yourself to work on it. And it takes discipline. It's very easy when you're busy and you have a lot going on, and you're in a meeting with a student, and the student says, well, what should I do next? And you just say, oh, you work on these, do that, right? Rather than thinking about the hard thing and what to actually do. So I feel like I've made that mistake a few times. Yeah.
Makes sense. So the next question is from Alex Denisov, who's a hobbyist. He says, first of all, I want to say thank you for the great compilers course. It was my very first intro to compilers, and it helped build a solid foundation. Then he asks, what would you cover in the course if you had built it from scratch today?
Yeah, well, so first of all, thanks for the kind words about the class. I'm glad that it was useful to you. Yes, if I was going to do the class today, I'm not sure what I would change. One of the reasons that the class is the way it is, and for people, just to say a little bit about what the class does, you build a compiler for a language, but not any language that we actually have in the real world. All right, and the reason, and it's a mix of features. It has a mix of some functional and object-oriented features. All right, and at the time that I did the project, that was not something that was represented in the real world. Okay. And it has a little bit different syntax, and everything's a little bit different. Everything's a little bit off from what you would normally expect. And the reason for doing that is to get people to really think about what the language means, so that it's not familiar, and so that they actually have to do some work mentally to understand what it is they're doing and get them to consciously think about the process. Because I think if you go and implement a language that you're very familiar with, you might not really work through in your head, how exactly these constructs work and what they mean. And if they don't mean quite what you expect, then you're forced to go read the manual, which of course has formal semantics in it, and you have to understand the formal semantics to actually figure out how the thing works. And so it's just a way of getting people to really, be intentional about the implementation and not just rely on intuitions that they've acquired. So if I was doing it again today, I'd probably I would need to pick a set of constructs that that are a little bit different from what are in any current language. So probably the obvious thing to do would be to add parallelism or concurrency, combined with some of the other things that I think are important for people to know. That's hard to do, I think, keep the project down to a size that you can implement in, say, 10 weeks or something like that. So that's the other huge constraint on something like that. But yeah, there are more languages now that kind of look like Cool, which is the language that's there, and I would probably need to update that. I'd try to make it a little bit more different. That'd be the one thing I would want to do. All right, too long an answer, sorry.
Next question is from Stefan Zaitsi, sorry for mangling your name, University College London. In your PLD19 interview, it was mentioned that you have thought about becoming a professional musician before pursuing a career in academia. Did your experience in science change your perspective on music or the arts? If yes, how?
I don't think my experience
or vice versa.
I don't think my experience in science changed my perspective on the arts much. I continued to be, an amateur musician for many years after I decided, to do computer science as a profession. I do think that the musical training, though, was actually quite helpful in my life as a computer scientist. In particular, having to get up and perform on a regular basis is a lot like teaching and a lot like giving a lecture. And so in many there's a performance aspect to talking to a lot of people, and I think the music, the long experience in music helped a lot with that.
Makes sense. Ben Zorn from Microsoft Research asks, what applications of deep learning to compilers are you most optimistic about?
Yeah. So hi Ben, by the way. Yeah, so the question is about applying deep learning to compilers, not the other way around. And so I think the question is, where can we where can we take advantage of deep learning inside of compilers? So I think the easy ones are that any place where you have a heuristic in a compiler, you can replace it by a learned model. And I think one of the clarifying aspects of machine learning, over the last few years has been that a lot of the heuristics we have actually aren't that great, and that you can actually, replace them with models and not worry too much about the exact design of the heuristic. Just let the examples, guide some kind of learned model. I think when you get into the correctness aspects of compilers, I mean, things that are correctness critical, there is a fundamental mismatch between the machine learning worldview where 97% is like awesome, and the programming languages view where 97% is like nothing. Okay, I mean, like 97% correct, you got something that's useless, right? And how we're going to bridge those two things, I think, is or whether we can. That's not obvious to me that can be bridged, but I think that's an interesting challenge. And worth thinking. I think that's worth thinking about. Let me put it that way. Because there's a really fundamental question there. I think there are some areas, and one obvious way to bridge it. Let's say, I shouldn't say it's obvious, but one way we could bridge it is maybe there are some places where we don't care about complete correctness. All right, like so I think some of the work that Kathleen inspired on probabilistic programming languages. There's places where you really have a statistical notion of correctness, and then maybe machine learning kind of techniques will be more prominent, in those areas.
Thank you. The next question is from Jubi Taneha. Again, apologies for mangling your name. University of Utah. There's a lot of amazing super optimization work done by your group, and it has inspired our research group here at Utah. Thank you for that. I wanted to know, what are your thoughts on making this technique an important phase of compiler development like other standard phases? What design principles would you advise to super optimization/synthesis researchers so that their tools are more widely used by a larger audience, especially during the compiler's compilation mode?
Right. Yeah, so I think we're still trying to figure this out. I mean, when I say we, I don't mean just me and my students, but I think the larger community of program synthesis is still trying to understand where the sweet spot for applications really is. And I think it's clear that the super optimization work at the low level, at the assembly code level, for that last bit of really exploiting all the tricky nuances of architectures is pretty useful, and a lot of the work at Utah has shown that. All right. And then the other big category of applications is essentially various domain specific applications where you have a few essential characteristics. Okay, so the most important one being that the programs are small. Okay, so if you have a domain where the programs are small, you can probably design. I think the experience has been you can probably design a synthesis technique for that. And then the other big problem is, can you get the data? Okay, so I mean, like for the kinds of style stuff that we do, it's all dynamic, so you need to be able to get the test cases to drive it. Yeah, so for super optimization for any of these techniques, again, I think there is the verification issue. All right, I think that's actually fairly solvable actually for a lot of the things that we're interested in. I think if we want to be more aggressive in using these kinds of techniques, and really, the big problem is scaling them up. And we still don't handle really large pieces of code very well. Okay, and probably the way that's going to happen is either through better specifications, because we have pretty limited ways of getting specifications right now for these kinds of these kinds of tools. And it's not clear that input-output examples is really, even if, while that's an easy thing, it's not clear that that's really, that there's enough information there to really drive, accurate synthesis at a high, for very large programs. So that's one issue. And the other is maybe, more restricted kinds of synthesis problems. I mean, maybe we don't want to try to synthesize absolutely every aspect of programs, and there's some other kind of structure there that we're going to live inside of, and we're going to fill in, details, but we're going to stick to some kind of recipe that makes the problem easier. Yeah.
So some kind of compositionality approach.
Yeah. Yeah. Well, I think some kind of divide and conquer approach probably is needed. Yeah.
Yeah. Thank you. Next question is from Tom Reps from the University of Wisconsin. He says, returning to guiding graduate students, you talked about when things go well and how you hope things to go. What do you do when things are not going so well? Thank you for doing this AMA, by the way.
Oh, you're welcome, Tom. What do I do when things aren't going well? I mean, it's, yeah, so this is, well, I guess I don't have an easy answer to that, and I want to say, I've certainly experienced that. Okay, where things have not gone well. What I've decided over the, I think I've changed my approach over time, and I generally have gotten more. I generally try to intervene more quickly now than I did in the past. So in the past, my approach was often to say, okay, let the student figure it out. I mean, ultimately they need to become an independent researcher, and maybe the way to do that is to let them just sit until they realize that they need to figure this out on their own, and I don't know what else to do. Okay, and I will say that approach actually works pretty well. Okay, I mean, so if you can kind of, basically what you have to do then is you have to keep, the student from getting distracted by other things. I mean, so, their tendency is to run off and do things that aren't research, or to work on the easy problems or whatever. And you have to kind of, set up a situation where they have no choice but to work on the hard thing and report progress on a very regular basis. So more frequent meetings, and really trying to get the focus on the thing that needs to be done, but also trying to make it kind of a quiet space so that they that there are no other distractions. Okay, and that worked pretty well. I would say I won't claim 100% success, but sometimes it would be quite a while, like months, before all of a sudden the light bulb would go on, and we'd start to see progress, and the student would gain confidence and get on the good trajectory. More recently, I've been more I've had more of a tendency to come in and say, hey, let's change what you're working on. So maybe this isn't exciting to you. Maybe you actually don't really like this that much, right? And let's consider a different project. Let's consider, let's really try to figure out what it is that would make you excited, to get up in the morning and do research. And I think that is one of the fundamental things. I mean, the student actually has to like what they're doing, or it's really hard. Right. And sometimes I think students will tend to sense what an advisor wants to do, and feel like they should want to do that even if they don't. And that can lead, that I think in my case has led to a couple of situations where students just weren't working on something they cared about, and that's extremely demotivating, right? And so when I realize that, I want to change that right away. Yeah.
Thank you. So the next question is from Sangeeta Chowdhury from Rutgers University. Since you've talked about not dismissing simple intuitions and ideas, how do you go from that simple intuition to a complete fledged project? There's a considerable gap between these two ends. And while you are filling this gap, how do you keep yourself motivated? Right.
So I don't know the answer to that. Okay. I think the So I stand by the statement. I think it's important not to dismiss the simple intuitions. And since Stoke has come up a few times in this AMA, that was an example of something like, why wouldn't this work? I mean, why wouldn't just brute force search over programs in some way be a good idea? And I first thought about that a long time ago. Okay, like I don't know, decades. And I didn't do anything with it for a very long time, but I didn't dismiss it, and I kept thinking about it, over the years. And eventually I had a student come along who I suggested this to them, and I had suggested it to other students who weren't interested. And the student actually went away and came back with an idea. All right, so they had like the next step. All right, and from there it developed fairly quickly. Okay. And that was actually pre-Stoke. That was work with Saurav Bansal and where we really were just enumerating programs. And all we could do was enumerate programs up to size 3. Like three line programs was the whole project. Okay, but like every single possible 3-line program that you could write in x86 assembly language. All right. And then it was several years after that before the next student came along, who was kind of interested in this, and he had a machine learning background and was, very familiar with all the kinds of, traditional machine learning search techniques, and said, well, why are you enumerating? That's really silly. Okay, we could do some kind of stochastic search. And so, there we go. Next project, right? So I think it's hard sometimes to take those intuitions and reduce them to to research problems, and it takes time. I mean, you just don't know when the inspiration will hit about how you actually convert that. I guess the lesson in there, and I'm kind of rambling a little bit, but the lesson is, talk to people about it. Like if you don't see how to do it, be willing to talk to people about it and bounce the idea off of them, and eventually somebody will say something that will trigger an idea.
So a related question from Julia Belikova from Northeastern University, a follow-up on not dismissing ideas. Were there cases when you thought something would definitely work, but it failed? Also, when in doubt, how do you decide whether to push further or give up?
Yeah. Okay. So there were definitely times when I had an idea and it failed. And unfortunately, I won't be able to give an example right now. I won't be, but I know that feeling and I can remember it quite well. That is not a bad thing, actually. Okay, because you definitely learn something when that happens, and often it will lead to another idea. Especially if your intuition or your idea was sort of aligned with conventional wisdom, and you try and it doesn't work. There's something in there. Okay. So paying attention to your failures as much of as your successes is very important. And I'm a firm believer in that you learn more from failure than you learn from success. And by the way, I've learned a lot. Okay. What was the second part of the question? I forgot.
Where did the question go? How do you know when to give up?
Well, when the referees won't accept your paper. I mean, it's kind of, that's like the time. Like you keep trying.
Well, it's ever before that, like before you get to the right part of writing the paper.
Yeah. So the great part about being a researcher in academia is that you can always move the goalposts, right? So if something turns out to be hard, you change what you're doing so that it's not quite so hard and you can actually do it. All right. So I'm not sure I ever completely give up on something, but sometimes the problem doesn't look quite like what we started with. Yeah.
That makes sense. Yeah, that's often my strategy as well.
All right.
We are at 2 o'clock, so drop dead time for this particular AMA. So we'll need to stop here. Thank you very much for all of your thoughtful answers. You can't, I don't think you can see it, but there's a whole bunch of people thanking you for your comments. I encourage you to go look at the thread afterwards. Yeah, thank you for your time. I really appreciate it.
And thank you very much, Kathleen, for being my questioner. It was a pleasure.
My pleasure as well.